Question 9. A and B react together to form an equilibrium mixture. Aqueous solution contains this many moles of A, containing this many moles of A added to this many moles of B. Equilibrium of each mixture contains this many moles of C. So, like I've done a couple of times if you've been watching the whole playlist, is I like to create a table. M, C, E. The moles, in this case of A is 0.25. The moles of B, in this case, is 0.25. The moles of C, we don't know, we're going to assume is 0. Equilibrium moles of C is 0.015, so we're going to add 0.015, and for adding 0.015 here, we're going to subtract 0.015, and here, we're not going to subtract 0.015, we're going to subtract 0.015 times by 2, because it's got 2 moles. No 0.235 for A, and 0.22 for B. 0.235 moles for A, 0.22 moles for B. At different temperature, 9.2, another equilibrium mixture contains this many moles of A, B and C, but this is the equilibrium moles. In this much volume of solution, calculate the value of the equilibrium constant Kc. So we know Kc is equal to products of reactants square brackets, remember. When we square bracket C divided by A square brackets times by square brackets of B squared. Now we want to find Kc here, but what they've given us here are the moles. We don't want the moles, we want concentration, so we're going to use the equation moles equals concentration times by volume. But we don't want the moles, we want concentration, so concentration is equal to moles divided by volume. So in this case, the concentration, well, we want it in moles per dm minus cube, so we're going to divide by 1000. So for the concentration of A is going to be 0.30 divided by 350, 0.350, 350 divided by 1000. For B, it's going to be 0.25 divided by 0.350, and for C, it's going to be 0.02 over 0.350. One second, guys. So now we've got this. Let's put it in the calculator. Or actually, we can just substitute that in now. Because now these are the concentration. This is the concentration of A. This is the concentration of B. This is the concentration of C. Substitute into the equation. So we get 0.020 divided by 0.350 divided by A, 0.30 divided by 0.350 times by B, 0.25 divided by 0.350 squared, and we get Kc is equal to 0.1. What does it want it to? 0.13. And then the units, that's going to be pretty hard to work out. we know we're working with mol per dm minus cubed, so we've got mol per dm minus cubed over mol per dm minus cubed to power 3 because it's 2 and that's 1. That cancels out and we're left with 1 over mol per dm minus cubed squared, which is equal to 1 over mol to power 2 dm to power minus 9. However, because this is on the denominator, is now going to be mol to power minus 2 dm to the power 9. No, not dm to the power 9. It's going to be 6. Yeah, 6. You don't square it, we times it. Dm to the power 6. Mol to the power minus 2 dm to the power 6, and kc is 0.13. And then 9.3 says suggest one expression for k can be written without the concentration of water. It's because H2O is almost constant. As it is much larger than the other concentrations. And then 9.4 says distilled water is added to this much of chloric ethanol, that's MR, to make 50 cm3 solution. Mixtures are to reach equilibrium. The value of the equilibrium constant K is 37. Calculate the equilibrium concentration of ClCH2CHOH squared. Okay, so that's the expression, which is nice that they've given it us. Calculate equilibrium concentration of ClCH2CHOH squared. So we're trying to find the concentration of this. Okay, so let's firstly find out the moles of it. .71 divided by 78.5. Equal to 4.71 divided by 78.5, which will give me 0.06. Now this one we're going to have to use algebra, so there's a reason it's 5 marks. It's not going to be that easy. Now we know the equilibrium amount of ClCH2CHO is going to be that 0.06 minus X, and the equilibrium amount of ClCH2CHOH squared is going to be X. Which makes sense, right? If you're trying to find out the equilibrium moles of ClCH2CHO, it's going to be this minus X. The moles of this 0.06 minus X, and this is just going to be X. Now let's try to put this in the equation. So we know the value of the equilibrium constant K is 37, so we can write 37 is equal to obviously we want the concentration, moles of concentration volume, so moles divided by volume. So it's going to be X divided by V over the equilibrium moles of this, which is 0.06 minus X divided by V. Okay. Well, now obviously the v's are going to cancel out, and we're going to be left with 37 equals x over 0.06 minus x times by this, so we get 37 bracket 0.06 minus x equals x. 37 times by 0.06, 2.22 minus 37x equals x. 2.22 divided by 38, 0.0, so we get x equals 0.058421. Now, how we answer the question? Well, what is the question? Calculate the equilibrium constant moles per dm minus cube of ClCH2CHOH squared. Well, we know that is just going to be x. No. In order to find the equilibrium concentration of this, well, we can rearrange it. So we get K times by no, we've got the answer. This is the yeah, this is the value that we've got. Of the number of moles. Yeah, this is the number of moles of ClCH2CHOH squared. And we know moles is concentration and volume. Concentration is moles. This divided by volume, which is 50 centimeters cubed, but we only divide by 1,000. So 0.50. That's where I got confused. 0.058421 divided by 0.50, and we get 0.05. Because yeah, 50, 1, 2, 3 is 0.05. 1, 2, 3, yeah. 0.05. And we get 1.17 moles per dm minus cubed. So I just want to go through this one real quick. So we find out the moles, mass of MR, 0.06. We know that, so we know the moles of this is 0.06. So we're going to say that is going to be, this is going to be X, right? If we want to find out the equilibrium moles of other thing, it's going to be 0.06 minus X. Construct the equation. X divided by V, the volumes cancel out, we get this, we get the X is equal to this. However, this is not the answer we're looking for. This is the moles, the equilibrium moles. These are just the moles, the equilibrium moles, so then therefore moles of concentration and volume. Concentration equals moles divided by volume, the moles divided by volume divided by 1,000, and then you get 1.17. That is not the end of question 9. In question 9.5, Figure 6 shows incomplete nucleophilic addition mechanism for the reaction of water with chloroethanol. So this looks good. Yep. Complete the mechanism by adding 2 curly arrows or relevant charges and any lone pairs of electrons involved. So what's going to be next? Well, we know now this oxygen has a negative charge. This oxygen is now going to become positive because it's transferred all the lone pairs of electrons. And what's going to happen is, well, you can see here OH and H2O. So this bond has to go, this OH bond. Then you're left with this, where the oxygen has a lone pair of electrons negative, and it attracts a H plus. And then that's it. So negative charge on oxygen, positive charge on this oxygen. This has to leave to form this OH. Then now the oxygen has a lone pair of electrons negative, and now bonds from the lone pair to the H plus. And then it says when an excess of water is added to ethanol, a similar nucleophilic addition reaction occurs. Suggest why this reaction is slower than the reaction in question 9.5. Well, this carbon in C double bond O is less electron deficient and why? Because it has a CH3 group attached, and this CH3 group has a positive inductive effect, hence higher activation energy, EA. So this carbon C double bond O is less electron deficient, yep, as CH3 has a positive inductive effect, therefore a higher EA, higher activation energy, therefore the reaction will be slower. And that's the end of question 9.